In the first video, I've talked about three distributions, about three discrete distributions. I've talked about three common discrete distributions. We talked about discrete. What you can take home here is that for the discrete uniform distribution, all events, all the outcomes are equally likely if the experiment qualifies or can be modeled as a discrete uniform distribution, then, and it has like 4 outcomes, then each occurs with probability a quarter, like that. The Bernoulli is just an experiment with 2 outcomes, a success and a failure. Know how to get the mean, the var, and then the binomial is a generalization of a Bernoulli and independent Bernoulli trials. They should give you a binomial, and also know how to solve those problems using binomial tables. Can't harm you if you know how to use them. And expectation, you should be able to do it. The val, kindly go through it. Then we are here on power saw. This power saw, this is a French name. I think he was a French mathematician, Power saw. And then this is the power saw distribution. Yeah, in this course, we are not going to derive how to arrive at this, but it can be done using some properties of power saw, which are not stated here. But what is good to know is that how do you write a power saw distribution? The probability mass function is written like this: e raised to negative lambda, lambda power x over x factorial. And also don't forget to tell us the range. It moves from x equals 0 all the way up to infinity. So we're saying that a random variable x taking on values from 0 all the way up to infinity is said to be a power saw random variable with a mean. Now this one just has one parameter, and the mean is called the mean, the lambda, and should be positive. And then the mass function is given like this, where this exponential can be approximated like this. And now this is a power saw, and we can show that it is indeed a mass function by summing all these probabilities from x equals 0 up to infinity, and then we see whether we can get one. But we shall need this result from elementary calculus, that for any real number, this should be true. From x equals 0 up to infinity, lambda power x over x factorial should give you exponential lambda. And then if you use that, and let us sum, and then see whether we shall get one. If you do the summation and you write the mass function there, you note that now this can be pulled out because it doesn't depend on x. And then you can sum this. So this is a sum to, no, it's not a sum, but you can use this result, yeah? Yeah, you can use that result. And this means that e raised to negative lambda times e raised to lambda, you get 1. Here there are some examples of power saw random variables. So at the back of our mind, we know that this power saw takes on integral values 0, 1, 2, 3, and then you can think of problems which can be modeled as the power saw, like a number of misprints on a page. They can be 0, 1, 2, or any number. The number of lucky guys living up to 100 years, maybe in a certain village. This could be 0, 1, 2, and so on. And then the number of wrong telephone numbers, dialed in a day, and many other examples. Maybe also the number of customers entering a post or a counter. So those are normally some of the problems which can be modeled as a power saw, and you can't exhaust them. So What about the mean and variance? So we can also get the expectation of power saw using the definition and some manipulations, of course. The same ideas, by the way, because here one would wonder why are we moving from 1. Of course, if we move from x equals 0, of course, when x is 0, this will be 0. That's why we moved from x equals 1. And also this can be simplified as we did for the binomial, if you remember. So x over x factorial can be simplified so that x can cancel, because this x factorial is the same as x times x minus 1 factorial, like this. Now, having gotten this, I now just need to manipulate, and then I say now, can I use the other result, which I showed you on just a page here? You need to use this, because now this one has x factorial, and also this has 0. So what you can think of a transformation, or change of variable, and then you say, let now this be y, so that you can have y factorial here, and also lambda raised to power y. And then if I said x minus 1 equals y, then it means when x is 1, y is 0. So this is the idea there. And similarly, you can also get the variance. So using the same idea, like what we did for the binomial, we needed this, we were using this expression, reason being that getting expectation of x squared directly, this guy is not so easy. That's why you have to move to look at this expression and then try to do some manipulation. I know you are asking why x equals 2, because when x is 0, this is 0. When x is 1, it will still be 0. That's why you can move from x equals 2. Then try to pull out what you can, because you have somewhere, let me see here, you have from x equals 2 up to infinity. We try to simplify this, yeah, so that this can cancel with x factorial, because x factorial is the same as x times x minus 1 times x minus 2 factorial. So this can get lost. When they do, I have x minus 2 down here, and I can try to pull out something so that I can have x minus 2 as well here, so that I can use the transformation, or I can change the variable, so that at the end of the day I can use the other result from elementary calculus. Now that's why I can now use this substitution. Kindly go through that. I'm sure if you can get this, then we know that this is the same as that, but we will need expectation of x squared, and that can be gotten. Then you substitute in the formula, and it should be good to go. Now I want to go through just 2 examples for this power, so you have to be careful, because what normally confuses students is someone can trick you, because this power saw can be looked at as modeling events which can occur in a particular time interval, and maybe also can be looked at as can model problems that can be maybe in a certain area or region, yeah. Like you see that there's a problem where someone was looking at the number of mice in one's acre of land. Yeah, so that's an area or a region. And then some of the problems, or in fact, most of the problems are in time intervals. Someone is interested in maybe number of customers are coming in at a particular time interval, like an hour to, or even a week, something like that. So for these problems, you have to be careful with the lambda given. Is it given weekly? And what does this guy want me to do? I'm computing probability. Is it also weekly, yeah, or fortnight? You have to be careful. The example here is not confusing, because we are saying that suppose that the average number of accidents occurring weekly on a particular stretch of highway equals 3. Calculate rapidly that there is at least 1 accident this week. Now, the probability is wanted in week, and also lambda was given in weekly. In this case, the lambda used to get probability will be the same as that given. And I don't think I need to go through it, because I said at least 1 can be like looked at like this. but it's easier to look at this as 1 minus vector of x equals 0, so that you just compute one probability and then you are good to go. But if you say that you're going to say x equals 1 plus x equals 2 up to n, because now this can go up to infinity. So you have to be a bit smart, and then you use some properties of probabilities, and then so that you don't lose, you use less time. There's a problem which was which I wanted, and it needed to manipulate. You can manipulate. I think it was the where to. Okay, let me go down. I think it's here. Telephone calls enter a school switchboard on average of 2 every 3 minutes. Now lambda, the average is given every after 3 minutes, but probability which is wanted is that of arriving in a 9-minute period. So this is where you have to be careful. So my lambda average was 2 but in 3, so you have to do some manipulation. If someone needs down this period of 9 minutes, then the lambda I'm to use is going to be 2 times 3, yeah. And even sometimes you may need to maybe even either multiply or divide, depending on the problem, yeah. So you have to be careful, because like if someone gives me the lambda or the average maybe for say a month, and the probability which is being asked is just for a day, then what do? Then you have to, this time I think, to divide so that you get the average for the day. So you have to be alert for that. And maybe what I can also say about power saw before I leave it, that sometimes you can also use tables, and even I attached a table for the power saw, very last page, yeah, of this lecture material. You can, and this example can be done using the table and even others, but I just wanted to single out this example. The average number of field mice per acre of a field is estimated to be 10. Now our lambda is 10. Find the probability that a given acre will contain more than 15 mice. We are lucky here, we don't have to do anything with the lambda, because the lambda given is per acre, and also probability required is for acre. Now, the tables, you know that this power source just has one parameter. So you just locate that table which is tabulated for this lambda, and you should be able to use it. But what is the problem? What do you want to do? Find the probability that a given acre will contain more than 15 mice. So I have to get x greater than 15, but it's the same as 1 minus probability of x less or equal to 15. So from tables, I should be able to get this. Let me show you. Let me run quickly to the table, and then I think it was the last page. I don't know. Yeah. So if you look at this table for the power saw, then it's also cumulative from x equals 0 up to r, and now this time they specify the mean as mu, and now this is the lambda, our mean as 10. So this is what we are looking at, and we will say that x less or equal to 15. This is the value. So something like that. Before I conclude this power saw, allow me to say something about the sum of a power saw random variables. If you have like two, like here, you have two. We are saying that. Hope you've gotten this one for the tables, because now this value from x equals 0 up to 15 is this one. kindly confirm, and then you should smile. Now, if I have two random variables, they have the distribution as power so, and each has lambda 1, the other lambda 2, then the distribution of the sum of those two random variables will also be power so with this. So kindly go through it, and then you convince yourself that this allegation or this claim, in fact the theorem, is okay. You will see how to prove this theorem or this in those who would do probability theory. You have a look at this using other techniques, maybe moment generating function techniques or probability generating function techniques. Yeah, and even also how to get the mean and variance. So that it could be easier even to use these two techniques, but this is not the scope of the course. Now, you can also look at power so approximation to binomial. I did this derivation in class. I don't wish to go through it now, but if for some reasons you can't see how someone can move from a binomial to power so, you have to see someone to assist you. But now the point to take home is that this is only valid when n is big, greater or equal to 20, and the p is less or equal to 0.5. When the p is small, under those conditions, you can approximate a binomial using a power saw. And also, we also use some bits of calculus, yeah, this elementary calculus, this result somewhere, and then we are able to see how we can approximate a binomial using a power saw. So look at that example. Now the geometric distribution is in fact in most of the textbooks, even that book I attached in Mwele, that reference textbook of Walpand and friends, they normally handle this with the negative binomial. They are close. In fact, negative binomial is an extension of this geometric distribution. Now, what's so special with this geometric distribution is that you do binary trials. You still look at success and failure, and then you just stop when you get a success. Yeah, you're just interested in just a single success, and when you get it, the experiment stops. And we don't know when it will stop, but there's a possibility of getting a success on the first trial. The second, you can get the success on the second, meaning that you failed the first trial, but you are successful on the second, or even you can have a success on the fourth trial, but meaning that the first three were not as good as you wished. Yeah, and now this is how we can write the mass function for the geometric, whereby x, these are number of trials. Yeah, and don't forget that when you're writing a mass function, you have also to tell us the range. Yeah, so this is the same, but we can also show that it is indeed a mass function by summing from x equals 1 up to infinity, and then you see whether that sum will give you a 1. You can pull out a p here as you see, and then you sum. This is a geometric series, a sum to infinity. You should be able to get this sum. Remember from senior 5, as you said, it is a first term divided by 1 minus common ratio, something like that. Kindly go through it, and you'll be convinced that it is indeed a 1. And now you could also formulate this geometric problem using the number of failures, not the trials, but number of failures. But I don't want to go through this formulation. Let us stick to the first one, because at least it is less confusing, but it's good to know that it can as well also be formulated using number of failures, yeah, before you get a success, or number of trials. So we are using trials, that it can be formulated. And the probabilities are going to be the same, but I suspect that the mean and variance, either both or one, may not be the same, but the probabilities are likely to be the same. You can look at it if you so wish. Now look at those properties, friends, and Mean and variance the same way. You can do it like that using the definition and doing some bit manipulation, but the confusion will come somewhere here. When you want to sum this, there is x, there is 2 raised to power x minus 1. Now the easiest way was to look at this as coming from somewhere, as coming from a derivative of this with respect to 2, which is true. And then instead of first derivating, then you sum. So this is allowed. You can, under some conditions, though we didn't state them here, but under some conditions, you can, instead of first summing, instead of first derivating, you can first sum and then you derivate the resulting sum. So that is allowed. So that's the trick which we used. You know, we borrowed this trick from, I think, calculus or analysis. So you have to use the result, yeah, of pure mathematicians, and then you do what you want in this field of applied mathematics. Now, that should be okay. In case you have a problem, say a friend or contact anyone who can assist you. And the same way variance can be done. Remember, this expression is so common. The same way, and then somewhere, I know you of course, here from x equals 1, it will be a 0. That's why the guy moved from x equals 2. And then also, instead of looking at this as a sum, you can look at it as a derivative, but 2 derivatives of this. And then you do what, as we did the other time, you first sum and then later you derivate twice. You should be able to get the expressions. In case of any problems, please see someone who can assist you. I think I can do an example here. I can do an example and then others you can go through them. Example 28, if 40% of people in a certain population have blood type A, find the probability that in a sequential testing of randomly selected people, the first person with type A blood is found on the 4th test. So if you see this 4th, then it means that you've done 4 trials. That's why it's 4. And even if you just substitute in the formula, you should be good to go. But now the interpretation here is that the blood group, you are failing to get the blood group people on the first 3 trials, yeah, and then later you get on the 4th. So it shouldn't be confusing. Please go through those examples, and we shall clear you where you have problems, or you can even see someone to assist you. And on that note, I should go to the negative binomial. Now, this negative binomial is just an extension of the geometric. In geometric, once you've gotten the first success, you just stop. But now, for this negative binomial, you may be interested in maybe the second success or the third, yeah, something like that. So that's why we are saying that in this case, we are saying that this is a generalization of the geometric distribution. It gives the probability distribution of the kth success, yeah, at the xth trial in a series of independent binary trials. So these are still binary trials, whereby each trial you can have a success and then a failure. And then you are interested in a success somewhere. But it's good to know that when k is 1, if you are just interested in just first success or just one success, then it will reduce to a geometric distribution. So that's the idea. And again, this is a second way of formulating it, but the first one is easier. So kindly go with this first one for simplicity. And in your book, there are no examples. We'll be able to add some too. Find the probability that a person tossing 3 coins will get either all heads or all tails for the second time on the 5th toss. So what comes to your mind now? Now that I'm interested in for the second time. The geometric was just interested in just first time and the thing collapses or stops. Now this means that your K is 2. 5th means now there are 5 trials. Now, how do you arrive at P as a quarter? If you toss 3 coins, there are 8 likely scenarios. I know you can sketch those scenarios. Please do. You observe that in just one scenario, you have all heads, and in another scenario, you would have all tails. And that becomes 1 out of 8 plus 1 out of 8 because of this all. And that's why you have a quarter. And once you have a quarter there, you just substitute in this. Sometimes we denote the negative binomial using B star in most of the books. That's because this is a negative binomial. It's not the usual binomial. And now if you look at this problem, because this guy needs the first strike, it could as well have been looked at as geometric, yeah? That's why we say that when K is 1, the problem is closed. In fact, it is a geometric, yeah? And in this note, that's what we are saying, that yeah, if you have a negative binomial and you are interested in the first success, then it means you are going back to the geometric. So these distributions, they are somehow linked, yeah, as I will say in the closing remarks of this topic. Then the hypergeometric is close to a binomial. We are still looking at 2 things, yeah. We are looking at a committee made of men and women. We are looking at defective items and non-defective. So you have to read this. I can't explain it fully, but and also another point maybe you can take home is that for this hypergeometric, for it, you are picking or you are sampling minus replacing. Yeah, whereas for the binomial, there's some kind of sampling with replacement. So that could be the difference, the main difference. Now, what you should take home, we are saying that this time, the calculation involved when using hypergeometric distributions are usually more complex than their binomial counterparts. That's true. If we sample without replacement, we may proceed in general as follows. Yeah. Said we may select n items from a population of n items in these ways. So this shouldn't confuse us because we showed it, we've seen these ways in the, was it chapter 2, the original material, first phase, these combinations and blah blah. And then we may also select other defective. If maybe you have m defective items, then these could be the ways, and also the non-defective ones. So the idea here is I'm interested in picking small n out of capital N, but now this capital N has defective ones and non-defective ones. So if I pick other defective one, then n minus other defective one, then over the total. So that's the idea of the hypergeometric. And just an example here, a committee of size 5 is to be selected at random from 3 men and 5 women. Find the probability distribution for the number of men on the committee and then the number of women on the committee. Now, our committee has to have 5, but we are having 3 men and then 5 women. It means the total is 8, yeah? The total is 8, but we are picking 5. Then they are saying that there are 3 men and then there are 5. So these are the possibilities. We could have no man, but then there will be 5 women. And this is the probability if you compute this. Then you could have 1 man and 4 women. You could have 2 men and 3 women. You could have 3 men and 2 women. Do you see any other scenario? Someone is saying maybe you could have 1 woman. But when you have 1 woman, then you shall only have 3 men, those will be 4. And the committee should have 5. So the idea is here, even this hypergeometric, we are looking at 2 things, defective and effective, men, women, something like that. And then this is the distribution for women. For men, men could be 0, 1, 2, or 3. 0 man, 1 man, 2 men, and then 3 men. So when we are computing for men, we are as well doing it for the women. So these are for the 5. That's why I think for the 5 women, it will be this. For the 4, will be here. For the 2, and lastly for the 2 ladies, you will be there. So you can go through this. It's not so confusing. The reference material has some examples, and you should smile at the end of the day. If you want to be challenged a bit, and you should also like to be challenged, by the way, look at how to get the mean and variance of hypergeometric. Yeah, I know on a good day, or one evening, one morning, you can be convinced that these are the expressions for the mean and the variance. And the last note was trying to compare hypergeometric and then the binomial, and then you can read that relationship. I want to make this video, I don't want to make it any longer, but there are a few points you can take home. Like now for the binomial event, it can also be extended to what we call multinomial. That's why in your lecture material or in that book, you see that they are also saying something about multinomial. And now this is arising. Sometimes you may not have just 2 possible outcomes. Like even that of throwing a die, you could look at it as a multinomial if you so wish, and in fact, if a die is tossed more than once, then that problem can be looked at as a multinomial, but we're not going to do that in this course. Also, this hypergeometry can be extended to a hypergeometric. Yeah. So the idea is that now these things can be extended, but for now we've looked at these 7 discrete distributions. They shouldn't be so confusing, and some have some links, some are standalone. Like now the power saw for it, it just doesn't resemble any of these other distributions. But now if you look at binomial, and then Bernoulli, there is a relationship that now this binomial is coming from a Bernoulli. Then if you look at geometric, it is still doing some Bernoulli trials, yeah. And now this negative binomial can be gotten from as an extension from the geometric one. So once you read these distributions and then you do the numbers, you will see that they shouldn't be confusing. Someone was like, how can you tell that now this problem is hypergeometric, this one is what? And so once you go through these examples, I'm sure you'll be able to tell the difference. Please do the numbers, and we shall see how we can have some live sessions so that we can answer your questions. But for now, I could say that topic 5 is well handled. See you.